Thanks. So my name is Ryan Bracey. I'm the Principal Process Consultant at Sedgman, and Sedgman is an integrated minerals processing company. So we design, build and operate minerals processing circuits for the mining industry. So today I'm just going to talk about some of the efforts and innovations we're working through at Sedgman to reduce the energy and water consumption of these processing circuits. So I just wanted to step back, I guess, because a lot of the people here are probably not in the mining industry and familiar with some of the water and energy demand of this industry. So I wanted to start on first 2 points, which is the grade and the demand. So on the top right-hand side of this, we've got a plot of the metal production and the requirements. And along the x-axis, we've got a number of different government policies at the moment. Included in this graph is a production of elements like cobalt, nickel, lithium, PGMs, etc. And they're all colour-coded by where they'll end up. So yellow's electricity networks, we've got EV, battery storage, wind, solar, etc. What we can see that any number of these policies is a massive increase in the demand from the 2020 baseline. And on the very far right here, this net zero by 2050, representing a 6 times multiple on the 2020 production globally, which is a significant increase. A massive complication to meeting this demand is the fact that we've got, on average, in the database of around 130 mines operating, resource discovery to production of a saleable resource is around 16 years. So it's a very long time from when it's first found to when you're actually selling something into the market. Then another major complicating factor is the grade. So what percent within the ground, within the ore body, is our actual valuable resource? And I've got an example here, which is the Escondida mine, which is one of the biggest operating mines in the world. It's located in Chile. It represents around 5% of the global copper production annually, and its financial year 24 head grade was 0.85% copper, which is really, really low, and this is considered a high-grade ore. So what that means is 99% of the material going into this processing plant ends up as waste. And the problem with waste in the mining industry, it's really fine, contains a lot of water, and it ends up in a big tailings dam, which we've shown here on the bottom right. And the scale of these mines is quite scary. So the Escondida mine runs at 12,500 tonnes per hour. So you've essentially got 12,000 tonnes an hour going into a giant dam full of water and fine particles. On a per tonne of copper product, we're looking at around 20 megalitres of water use and around 4.2 megawatt hours. So very, very significant. One of the other complicating factors on this water and energy intensity is what we call liberation. So on the bottom left here, we've got a mineral liberation analysis image of a rock. So this is basically an X-ray of a rock, and the colours, the different colours are representing different minerals within the rock. On the bottom right, we can see the scales around 200 microns, so this is already quite a small particle. The orange colours within this rock is chalcopyrite, which is a copper-bearing mineral. So if we wanted to get the copper out of this rock, we have to grind that whole thing down to, say, 50 microns or less, so then we can extract the chalcopyrite from the rest of the gangue material. Now, this process usually takes place in the crushing and grinding circuit, and when you add that up across the whole mining industry, the overall energy is reported to be up to 2% of the global energy use just for comminution. If we're looking at a specific concentrator or mine itself, depending on the ore type, this can range from 36% to 47% of a mine's energy. So on the top right of this slide here, I've just simplified a concentrator design. So we've got crushing, grinding, recovery and regrind, and then we've got the tailings dam, which almost 99% of our material will end up, and then our final product. And this is for hard rock mines, so copper, gold, spodumene for the lithium, for example. So what's Sedgman doing about this massive problem that's facing the global industry? If we look along at the top right of our simplified flow sheet, we've got a number of initiatives and novel technologies that we're looking to fully replace the comminution module within these circuits. So some of these look like the EDS multi-shaft mill, comminution reimagined, and HPGR and air classification circuit. In terms of energy saving, it's in the range of 30 to 70% for these technologies, and they also operate completely dry. So we're reducing the amount of energy and water input when we can include these into the design of these concentrators. At Sedgman, we've got a strategic initiative to partner with these innovators and OEMs early to fast track their development through the technology life cycle. So this can take a number of different forms, from early stage test work in the laboratory for low TRL technologies, all the way to on-site pilot plants. And then our overall aim at Sedgman is to have a full-scale implementation so we can get these technologies into circuits, saving energy and water. We've also investigating a number of other technologies that operate outside of the novel comminution space. So focusing again on the flow sheet in the top right, ore sorting and coarse particle flotation technologies, so after crushing and after the novel comminution. And the general theme of both of these technologies is to reject waste from the circuit before it's been ground down really fine and got all of the water associated with it. So you'll notice that both of the ore sorting and coarse particle flotation have a coarse reject stream associated with them. The technologies in this space are bulk ore sorting. In the coarse particle flotations, it's NovaCell and HydroFloat technologies. And we're looking at mass rejects from 50 to 70% for these technologies. One of the other main goals of a coarse reject material is that it's still kind of in that stone size range. So it's easy to dewater, we can stack it dry, and it doesn't end up in large tailings dams having massive environmental impacts on a long-term basis. At Sedgman, we also look at the same kind of innovation model where we partner with mining companies and innovators early to fast track their development. And some of these technologies here are at a very high TRL, and we're including them in our new designs that we're using in our project and study work. So overall, at Sedgman, we're aiming to maximise the mineral production sustainably through innovation and collaboration. So thank you.